So we start?
Sure.
Yeah. So let us start today's seminar. Today we have Professor Ben Davison from the University of Edinburgh. He will talk about strong positivity for quantum cluster varieties.
Great. Well, thanks a lot for the invitation. It's always a really great honor to speak here. Yes, and always a great pleasure to come to Seoul. And I'm looking forward to my week or the rest of my week here. So yeah, today I'm going to talk about almost the entirety of the talk is going to be based. No, the entire talk is going to be based on joint work with Travis Mandel from now a couple of years ago on the strong positivity conjecture for quantum cluster algebras. Yeah, let's just dive into it. So cluster algebras are a certain class of algebras that seem to come up in very far apart branches of maths. And I think that's partly because despite looking kind of beastly, they do have a simple, rather combinatorial definition. They come from quite an elementary structure, really, and somehow, to me, a surprise that the literature regarding them is only a couple of decades old. So the combinatorial input is a quiver, which is just algebra speak for a directed graph. All of my quivers will be finite. So I'll have a pair of finite sets, Q1 and Q0. Q1 you should think of as being the arrows, and Q0 as being the vertices. And between these two finite sets, we have two maps, S and T, standing for source and target, which takes an arrow to its source or its target here. So I write it this way as opposed to drawing a picture, because I want to emphasize that this is really just combinatorics. It doesn't really matter how you choose to draw these things on a pad of paper. In essence, it's just a pair of sets and a pair of maps between them. And one of the rules of the game in cluster algebra land, though it's a rule that halfway through the talk will start breaking, is that quivers never have loops or two cycles. So a loop is a cycle that consists of a single edge, i.e. it's an edge that has the same source and target, and a two cycle is a two cycle. So because of these conditions on my quiver, the quiver is entirely determined by another rather down-to-earth piece of data, namely the adjacency matrix. So that's a matrix B, whose ijth entry is the number of arrows going from I to j minus the number of arrows from j to I. And precisely because there are no loops or two cycles, that uniquely determines my quiver. And it's important, though not super important for when you're trying to give a talk on the subject, that there be a subset of frozen vertices. And for historical reasons, we label the vertices 1 to m and the unfrozen vertices 1 to n, despite the fact that n comes before m in the alphabet. And it just seems to be too late to change that convention, so I'm going to stick with it. Right, and L for lattice is going to be the lattice. The lattice with the basis spanned by the vertices of my original quiver. Okay, so out of this combinatorial data, I'm going to tell you how to build an algebra. And as an algebra, it's a sub-algebra of a really basic algebra, which is just ZL. So this is a Laurent polynomial algebra with one variable for each of my vertices. And the way that this cluster algebra is defined is as a sub-algebra which membership is recursively defined. And we start off with something called an initial seed. And the initial seed are just the standard generators of this Laurent polynomial algebra. And then out of that, I'm going to tell you more things that belong to this algebra. So for I unfrozen, And that's one of the rules of the game, that you can only mutate at unfrozen vertices. Then I define mutation in what to the experts might look perhaps like a slightly strange way. So mutation at I is a two-part operation. Firstly, I leave all but one of the elements of my seed alone. And the ith one I replace with a two-term thing like this. So I replace it with, here I'm using this kind of convention that where you see a bold y with a vector, so some elements in my lattice, that means, so ye1 just means y1, but ye1 plus e2 means y1 times y2. So mutation at I replaces yi with a sum of monomials. And then there's a second part of mutation, which is less important, which is I just do a basic substitution of my exponents, which I don't really want to focus on unless people want me to. So it looks rather benign. I just leave all of the monomials alone and replace one of them with a sum. And then alongside this, or in parallel with this, there's a mutation rule for quivers, which I can say in words, but it's not super important. I'll just say it in words. So what one does is for every arrow that either has source or target my vertex I reverse the orientation, and for every path of length 2 passing through I in the original quiver, I add a new arrow going from the source of that path to the target of that path. And then there's some cancellation of 2 cycles. But again, it's not hugely important to memorize that. So AQ, which is the cluster algebra, is the algebra generated by all of the cluster monomials. That is, all of the elements in my Laurent polynomial algebra I can get via iterated cluster mutation. This is where things get interesting. This is where things get complicated, because I'm allowed to mutate forever. So you see these sequences. So this is the mutation at I is something I can do for any sequence of vertices. So in particular, there are a priori infinitely many of these mutated cluster monomials. And so, as you can imagine, in complete generality, it's rather hard to work out what does this subalgebra look like, what are the things that are in it, and what are the things from this larger ambient algebra that are not in it. And it's this infinite recursive procedure that makes life interesting / difficult / rewarding. Okay, so that's the definition. And as I said at the beginning, it's kind of elementary, up to the trick of cheating and not drawing this mutation rule on my slide. I can actually get the definition onto a single slide. So despite these things being very rich, they do have this rather elementary definition.
Can we pause for a second?
Of course.
Some Zoom audience says that they can't read the screen. So one thing we can do is you log into the Zoom and screen share.
Yeah, let's try that. How do you want to do that?
I can give you the link again.
Yeah.
You have the link?
Well, you sent it before, right? No, I'm not connected.
Let me send you again.
Yeah.
Sent it? the one below, geometry algebra.
Is there a
Yes. Just click the link.
Recording in progress.
Um, Thank you.
What's happening? Is it muted? This has to be fine.
Now it should be fine. I've switched off the sound on the laptop. Okay, and I want to.
I guess the Zoom audience can't see where you're pointing at, but I think there's no other way.
Yeah. Minimize that. Okay.
Yeah, good.
And I can stop control it. Yes. Okay. All right. Well.
Yeah.
That should be better. Cool. All right. Well. Yeah. As I was saying, the definition is sufficiently elementary that up to leaving out this mutation rule, I can get it onto one side. But the structures we get are incredibly rich and show up all over mathematics, and also have some kind of deep mysteries that we're trying to uncover. So what are the general results? Firstly, the first result that one needs to check is that this definition actually makes sense. So why might this definition not make sense? It's if I go to here, in this second term, I have a I have a minus sign. So what you're seeing here is some rational function in terms of the original cluster monomial. So if I just do one mutation, it's clear that everything is fine. I've got evidently a Laurent polynomial here. But if I take an arbitrary Laurent polynomial and not just a Laurent monomial and try to invert it in this ring, then in general, you should expect to have some problems. You should expect to not stay within the land of Laurent polynomials. But the happy fact here is that you do. So iterated cluster mutation stays within the ring of Laurent polynomials. So that is, the definition makes sense. So if I take an original Laurent monomial here, I guess I want the exponents for v to all be positive, and I mutate it any which way I like, then what I get out in the end is some Laurent polynomial with coefficients where those coefficients belong to the integers. So that's something that was proved at the sort of outset of the subject by Fomin and Zelevinsky. So in the background, though I'm not going to talk about this a lot, is a kind of hoped for, and in many cases proved, categorification of the whole picture. And one sort of shadow of that is that one expects that the cluster monomials are linearly independent. That is, they're meant to correspond to distinct classes in some simple classes in some Grothendieck group. And that kind of hope, that kind of dream or desire was proved in a theorem due to all of these people. Okay, so here's the one that's closer to the current topic today. That's positivity. So again, this is something that comes from the kind of original hopes or the original motivation of the subject. cluster algebra structures were originally introduced in order to investigate something called total positivity in coordinate rings on certain affine varieties associated to quantum groups. So in particular, for the subject to be a good subject, for the subject to be doing what it's supposed to be doing, one would expect or hope that these coefficients are positive. And this was proved by Lee and Schiffler some years ago using really pure combinatorics. And this one brings us even closer to the topic today. This is something called strong positivity. It's called this because up to a little bit of a couple of lines of extra work, it implies positivity. Grosshack and Keel and Kontsevich proved the following, that the cluster algebra AQ, defined on the previous slide, is a subalgebra of some naturally defined, possibly bigger, though sometimes not bigger, algebra called the middle cluster algebra, where this cluster algebra has a basis of things called theta functions, which are defined using techniques that we'll see later in the talk that come from the study of mirror symmetry, especially in the program initiated by Gross-Hacking and also studied by Keel and Kontsevich. So this AQ mid has a basis of theta functions indexed by some subset of the lattice, possibly the whole lattice, sometimes not the whole lattice. It contains all of the cluster monomials, but it might contain more. So these theta functions might be a strictly larger set than the cluster monomials. And the structure constants with respect to this theta basis are positive. So like I say, you can get out of this last statement, the positivity statement of Lee and Schiffler, but this is a stronger statement. It's saying not just that the actual terms in the algebra, not just that the natural basis of this algebra have positive coefficients, but also when I multiply them together and re-express what I get in terms of the structure constants for my algebra, these also are positive. So this is a really strong property that holds for general Q. So in this subject, really the cases that are sort of solid ground and we know have to make sense are when Q is finite type, so ADE. But this is a proof for general Q, and that's where things get a lot more wild. But yes, yeah, this is a result for general Q. So far, this is all.
Just to clarify, is linear independence over Z?
Over Z, yeah. Yeah.
So what is strong? What's the difference between the two?
So the strong positivity statement is a result about the structure constants for this algebra. So the algebra has a basis, and given my theta functions, the theta functions contain the cluster monomials, and the positivity result says that those cluster monomials, which are all written as Laurent polynomials in this Laurent polynomial ring, those cluster monomials have positive coefficients.
Strong positivity implies positivity.
Yes.
Don't you have to either restrict to some class of reverse Q or allow formal Laurent series?
No, not for this. No. So if you want something, if you balk at this, if this is something you object to, and you say, I want a basis of theta functions, one for every element of L, then you can go ahead and do that. You get a larger algebra, and the theta functions corresponding to elements of L that aren't in here will be formal functions. But for what's on the board, there's no need to have anything formal.
So, may I ask a question about I think maybe you just answered that, but I don't get it. It's like when you construct those theta functions, usually you need a formal parameter.
Yeah.
And that formal parameter does not appear in this.
Yeah, so when you construct the theta functions, a priori, I mean, we'll see it in practice, but a priori, there might be infinitely many broken lines contributing
Yes.
infinitely many terms, at which point you might have, and in fact, you generally will have a strictly formal function. The definition of this thing is take exactly those theta functions that aren't formal.
Okay.
And the first point is what guarantees you that that will at least capture the cluster monomials. At least if I stay within the land of cluster monomials, I'm not going to have to capture anything strictly formal. Okay, so the title of my talk makes some promise that there's going to be some quantum version of the above coming down the track. So how to quantize cluster algebras, and again, how to do it in a single slide is really the challenge. Okay, so remember B was my signed adjacency matrix for my quiver. So if I apply B to EI, the ith basis elements, I get this difference between the number of arrows going out of I and the number of arrows going in. And I just define B to I to be that difference. Okay, so then for an arbitrary monomial y to the b, and again, I think I want to insist that the entries of v are all positive here. The sort of the initial step in my mutation where I replaced my my yi with a two-term thing. Well, because now v might have a large entry in the ith place, I won't get two terms, but I'll get some binomial expansion. And the binomial expansion will keep track of what is the ith entry in v, and yeah, I'll get a binomial coefficient as I sum through v plus multiples of beta I. So this is just a result of the definition I gave you of cluster mutation, along with the fact that it's an algebra morphism. Okay, so that's so far still classical. But how do we quantize? Well, the thing is that there's a kind of well-worn path when it comes to quantizing binomial coefficients, which I can explain to you very quickly. So this nt, which I call quantum n, is it's a quantization of the number n, which is just a fancy way of saying it's a Laurent polynomial in one variable, t, such that if I set my quantum parameter to be 1, I recover the thing I'm quantizing. So as long as I haven't made any mistakes here. If I put t equals 1 here, I get back n, but this is some richer thing. It's a Laurent polynomial.
Is UI prime the same as before?
Yes.
Or why that form?
Yeah, so before I defined, maybe I'll go back. I gave you the formula for what happens if I apply mu I prime to one of my generators of my Laurent polynomial ring. So if j is not equal to I, it leaves it alone. If j is equal to I, it replaces it with a two-term thing. So now if instead of having yj here, I have some more interesting monomial, so some product of yj's for j sometimes equal to I, sometimes not. Each time this operator sees a yi in there, it replaces it with this expression. And each time it sees a yj from j not equal to I, it just leaves it alone. And so I end up, in general, getting a binomial expansion. Okay, so that's quantum n on that first sign. Quantum n factorial, well, n factorial is just the product of the numbers from 1 to n. And if I just quantize all of them, that's my version of quantum n factorial. And again, if I put t equals 1, then I'll just get back usual n factorial. And then, depending on where you go to school, I guess, this is something that we all learn in school, that n choose m can be written as a quotient of different factorials. It's n factorial over n factorial times n minus n factorial. And if I just quantize everything in sight, that gives me quantum n choose m. So that's some Laurent polynomial in T, such that if I put T equals 1, I get n choose m. Yeah, it's a sort of richer object. Okay, so given that cluster mutation, at least when I do it once, it's given by this very simple operation that just involves binomial coefficients. And here we have, I hope, what seems a fairly natural way to quantize binomial coefficients. You could hope, well, why don't we just replace my rule for cluster mutation with exactly the same rule, but I quantize these binomial coefficients. What's wrong with that? Well, quite a lot, really. It's not a ring homomorphism. So if it's quite easy to check that this is just not an algebra homomorphism, and so that's not going to work. But it's somehow quite easy to fix. So what we do is we find some skew-symmetric form lambda satisfying this condition. So this condition looks like it might be difficult to satisfy, but it's actually easy because you can always add more frozen vertices and make life easier. So just take it from me that one can always find such a lambda. And then we do something which might look odd, or if you've done lots of quantum algebra before, will look like the obvious thing to do, which is in the Laurent polynomial ring, we slightly quantize that too. So before, we would have had y to the v times y to the v prime. Is this equal to y to the v plus v prime? And then pulling them out the other way, we get that that's also equal to y to the v prime times y to the v. And once you're in the quantum world, it's just not natural to have those variables commute. Rather, you have them, one would normally say q commute, but here I'm using the variable t as my quantum parameter. So you have them t commute by imposing instead this relation. And then this formula for quantum cluster mutation does make sense and is also the right formula. Okay, so let me just spell out how that definition now goes. So we have L, and now we give it a skew-symmetric form, omega, which could come from anywhere, but in the end for us will come from a quiver. And we define the quantum torus as something having a z basis or a z t inverse basis given by the same monomials as we had before for the Laurent polynomial algebra over z, but now coefficients are in this Laurent polynomial algebra in T. And we do the thing that the box on the previous slide, the last box on the previous slide, was telling us we're probably going to have to do, which is instead of having these things commute in the obvious way or multiply in the obvious way, we make them t commute by introducing this extra factor here. Okay, so now choosing my skew-symmetric form to be this lambda, I get this quantum torus. And now, with that little bit of preamble, the definition is really the same. So I start with this quantum torus, which is defined like so. And while this ambient ring is it's maybe one step less elementary than the usual Laurent polynomial ring, but still something that's easy to play around with. What makes the quantum cluster algebra, which is a subalgebra, a bit difficult or rich or interesting, is that deciding on membership is going to be difficult. So here are the rules for membership. Firstly, we put in all of the original generators from before. So the Y's, the EI's, the sort of obvious generators of this Laurent polynomial ring, but also all iterative mutations. So for any sequence of vertices, I can mutate via, I mean, this is precisely the same rule as before. It's just it's happening in this ring instead of the usual Laurent polynomial.
What else lambda?
Yeah, lambda, I kind of breezed past this. So lambda is this skew-symmetric form which satisfies this maybe quite hard to pass in real time relation. And the point of this relation is that if I q-commute or t-commute my Laurent polynomial ring via the rule given by lambda, this sort of basic guess for what the right formula is for quantum cluster mutation is a algebra homomorphism.
Omega satisfies this condition.
So I'm just setting omega to be lambda. So here I've defined what the quantum torus is for an arbitrary omega, and now I'm going to set omega to be lambda. Okay, so the rules are exactly the same as before. It's just that the ambient ring that I'm performing those rings in, performing those rules in, is a little bit non-commutative. Yeah.
So in this case, when you write these rules, y to the power sum over something, the order is important.
So like I said earlier, I'm presenting things in a slightly odd way, maybe marginally odd way, and I'm doing that so that I don't have to talk about orders. So if so for example, if I decided to write this, if I'd broken up this vector into its constituent parts, so a1 times e1 plus b1, a1 plus a1 times e1 plus a2 times e2, blah 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 blah, and then written this thing out as y1 to the a1 times y2 to the a2, then you're right, I would have to start to think, well, hang on, which order do I want to put these in? Because depending on which order I choose, there'll be an overall. But I've not done that. I've stuck everything in the exponent.
Oh, okay.
And then life becomes much easier.
So here you don't split them up as a product.
Definitely don't want to split them up.
Okay.
If I started splitting them up, then I would have to have some overall horrible
Sure.
t factor here. And,
Like the normalized part.
Yeah. Some basis,
yeah.
but some generators, right?
And also, if I refuse to split things up, as I am going to continue to,
Yeah. Then life is happier.
life is happier, and all of the coefficients. I mean, here it's kind of obvious because t doesn't even make an appearance, but all of the coefficients will be invariant under t goes to t inverse, which again gets broken badly if you. Yeah.
Basically, you're splitting using the multiplication over there so that you have a t minus omega of those exponents when you're trying to split these things up, right?
Yeah, if I think of this thing as, well, the natural thing, and then there are a bunch of different ways to split it, one for every permutation, and I think of all of those as being equally unnatural, and each one will introduce an overall t factor, and they'll be different. But like I say, it might look perverse, but there's a reason for me presenting this.
This algebra should have more generators than the classical.
I will see.
Because previously, like if yv, then you can break down it into just product of yti's.
Yeah.
But here, basically yv, you cannot break down into like those ei's in a canonical way.
No, you'll see they're kind of the same size up to changing the coefficient ring from z to zt.
Then this yi's, they have nothing to do with t in this case.
Yeah, t doesn't make an appearance. Yeah, t doesn't make an appearance yet. So if I just do one mutation, t doesn't appear. But once I do more than one, t can appear. And it's in this kind of ironing out.
Oh, I see. Yeah.
Yeah, like. Yeah. Okay, how am I doing for time? Presumably, actually, horribly. No, okay. I mean that's manageable.
You can actually go over time.
Yeah, I mean,
I confirm that there's no other schedule.
it's fine. I'm pretty relaxed about not getting to the end because people are asking lots of questions. I'd rather that than get to the end and lose everyone. So whatever. It's your seminar, not really mine. That's my point. Okay. So just as I had a board of general results for general cluster algebras, I'm going to give you an analogous board, but with some different names for quantum cluster algebras. So again, the first thing you have to check is that this definition makes sense. When we, sorry to, I know this is annoying for some people. Here, again, we've got this minus here. And if we're just doing a single cluster mutation, it's no big deal. This is this thing is a monomial in this ring, and no harm done. But if some of these y to the ek's themselves have been replaced with two-term Laurent polynomials, and we start trying to write out things like this in terms of the original basis, that does involve taking dividing by a true Laurent polynomial, which feels doubly dangerous in this quantum Laurent polynomial ring. So the first sort of reassuring result is that nothing bad happens, i.e. the following. For any sequence of unfrozen vertices, if we iteratively mutate at them, we get the following, that the mutation of each of our starting variables along the sequence is a Laurent polynomial in our ring. So it still lives in the ring that everything is meant to live in. But now, remember before, the coefficients were, of course, integers. Now they've been replaced with Laurent polynomials. So, I mean, recall that the ambient ring here is the ring of Laurent polynomials with coefficients in here. So this is all sort of as it has to be. So that's good. It means that the quantization of the story does actually make some sense.
Also, the sum is finite.
Yeah. Okay, so this is a result of mine from, it's from a while ago now, and it sort of predates the work that I'm going to talk about with Travis and uses slightly different techniques, and I don't really want to talk about the proof because it's takes us off track, but just as for the classical case, it was possible to show that each of these coefficients was not just an integer, but a positive integer. One can show here that each of these Laurent polynomials in T don't just have integer coefficients, but have positive integer coefficients. And there are, moreover, Lefschetz. So I'll come to that at the end, depending on time. I mean, it seems less and less likely. But Lefschetz here means that these polynomials, which themselves appear as coefficients here, are sums of quantum numbers. So yeah, I'm going to, recall. So the quantum numbers were these Laurent polynomials. And of course, if I just take sums of these, then I get things with positive coefficients. But not every Laurent polynomial, even Laurent polynomials invariant under T goes to T inverse, can be written as a sum of quantum numbers. And the kind of bonus material in this proof of quantum positivity was that indeed these coefficients can be written as Lefschetz type polynomials.
Non-negative sums of the...
Yeah. That if I write them as linear combinations of quantum numbers, again, there are no negative coefficients, which is stronger than saying if I just write them as Laurent polynomials, there are no negative coefficients.
Is it also either odd or even?
They're also always either odd or even. Yeah. So when you put those two things together, what this is saying is that these Laurent polynomials are unimodal. So you throw out either the odd or the even coefficients because they're all zero, and you get what looks like a kind of bar chart, which is symmetric around the origin. And what this is saying is that it's unimodal, so it goes up and then it comes down. There's no gap, there's no valley in the middle.
This is true for any skew-symmetric initial product.
Yep. Okay. So I will continue. So, like I say, I don't really want to talk about the maths that went into that proof at all, because this talk is about something different. But there is some overlap. And the overlap is refined DT theory. And I'm going to sort of introduce as much of that as I need and no more. So one, again, elementary, but somewhat hard to sort of motivate until you get to halfway through this slide. Operation that plays an outsized role in refined DT theory is something called Ptic exponential. And I'm not going to assume anyone here knows what those are, though I know that some of you do. So here's the definition for you. Let f be a formal power series in all of these variables. And I'm going to treat t as being somehow special, because t is special throughout this talk. So it's some formal power series, meaning that I have a whole bunch of coefficients, and those coefficients keep track of they're the coefficients for these monomials. And what Ptic exponential does is something odd. It takes those coefficients, which previously were just coefficients in my formal power series, and turns them into exponents in a infinite Euler product expansion. And why you would want to do this is not immediately obvious, but it will become obvious in just a moment. And this is just some notation that keeps things neat and tidy. So math BBE is going to be given by the following operation. First, I take my formal power series, then I multiply it by this thing, by this expression, and then I take the Ptic exponential. And for now, just think of this as something that makes all of the subsequent formulas for the rest of the talk much more compact. Okay, so where does Ptic exponential really come from? Well, it comes from looking at characteristic functions of multi-graded vector spaces. So let V be a graded vector space such that its characteristic function, i.e. the function, the formal power series where the coefficients keep track of the graded dimensions of this graded vector space. Let's assume, well, that this lives in here. I'm not going to allow this thing to be, I'm going to assume that it has finite dimensional graded pieces, for example, so that this characteristic function really does belong to this ring. And the plus here means that the constant coefficient in all of these sets is 0. So if that means that if I look at the graded piece corresponding to 0 in here, that's empty. So it's some sort of positive grading to this V. Okay, so let it be such a vector space with its characteristic function. Then here's the punchline. If I take the free supercommutative algebra generated by V, if all of these coefficients are positive, then that just means the free commutative algebra generated by V. I take the free commutative algebra generated by V, and take its characteristic function. That's the same as taking the characteristic function and taking the Ptic exponential of that. So that's really the origin of Ptic exponentials, as far as I'm concerned. It's a kind of decategorification of passing to the free supercommutative algebra generated by something. And it makes, like I say, this notation, it makes formulas a lot more complex. It makes them a lot simpler. So here's a bigraded vector space, V. So it's graded by, well, I've written it as a direct sum, so it's got one grading that's kind of baked in, but it also has a cohomological grading. So the nth graded piece is the cohomology of point mod GLN, but I've shifted it all down by n squared in terms of its cohomological grading. So the cohomology of point mod GLN, this is infinite dimensional. It looks like the ring of symmetric functions in n variables, but at least the cohomologically graded pieces are all finite dimensional. So this characteristic function makes sense. And what's more, something somewhat remarkable happens. I mean, it looks like a bit of a monster, it's obviously infinite dimensional. It's got infinitely many pieces. Each one of them is infinite dimensional. So it looks kind of hard to work with. But in fact, it's not really. Once you have these operations and you have to use them, you just take this formal power series, the one that's just Z, so it has only, I mean, it's pretty much.
Chi t is a special element.
Chi t is the characteristic function. So chi t v equals the sum experimentation nv like the dimension of the n the graded piece of v. Can you see that? Sorry. And t m z. Yeah, so this thing, which although it's kind of natural, it's the cohomology of the stack of all finite dimensional vector spaces, if you like. So it's maybe a natural thing to consider. But what's more, it's really a simple expression when written in terms of the Ptic exponential. It's just this math BBE applied to this very simple formal power series. So that's the first calculation, and that's called the quantum dilogarithm for people who are trying to.
Okay, G is one variable or
So
G.
yeah, so here my R is just 1. So the next example is in many ways actually the same example. So if I take the space of n by n matrices acted on by GLN, take its cohomology. Well, this space is equivariantly contractible to a point. So this cohomology and this cohomology, they're actually isomorphic. It's just that here I don't impose this cohomological shift. So that changes the t degrees of everything in sight. But no matter, when I take the characteristic function of this bigraded vector space, again, I get something really simple. I get this math BBE, but applied to this very simple formal power series. So Z times T inverse. Okay, so although they kind of look the same, I'm going to argue that they're really different. And the point is in this kind of this sign here that gets, so you see, this sign is saying that T plays a very special role for us.
What's the dimension of H point divided by GLN?
What's the dimension of
H, the corresponding. Yeah.
dimension of this?
Yeah.
So
H.
as a stack, it has dimension minus n squared.
Cohomology.
So the cohomology of this is infinite dimensional.
Then
But each cohomologically graded piece is finite dimensional.
then how to define dimension there?
So H point mod GLN is isomorphic as a ring Q P1 up to Pn, where Pi has cohomological degree 2I. So because all of these generators have a strictly positive
How
cohomological.
to define dimension in the cells here?
Well, this is an infinite dimensional vector space, but if I restrict to the part of it that has overall degree some fixed number to n, it's finite dimensional. It's like, well, if I put n equals 1 and look at this is infinite dimensional. But what its characteristic function is is, well, there's one piece of cohomological degree 0, which contributes a 1. There's one piece, i.e., piece spanned by P1, which has cohomological degree 2. One piece spanned by P1 squared, so on, which comes out as 1 minus T squared minus 1. So you see, in action, the passage from the characteristic functions of free commutative algebras generate these infinite Euler product expansions.
So then this is two indexes, this n and then also the.
Yeah, these are both bigraded. Yeah.
Okay,
So the first grading, the one that
okay.
Z is keeping track of, is this n.
I didn't catch that. Could you try again?
That's my watch. Sorry. And the T is keeping track of the cohomological grading. Okay, so despite the fact that the answers kind of look the same, except for this factor of T that appears, really they're very different. So it's bound up in partly in this sign here. And the basic idea is that it's the following. That T is keeping track of cohomological degree, and if I take the free supercommutative algebra generated by something in odd cohomological degree, that's an exterior algebra. So its characteristic function might end up looking something like this. Whereas if it's an even cohomological degree, it looks more like this. I guess. And I call the first case fermionic and the second case bosonic. But the connection with dt invariance is that these two calculations are the calculations of the dt invariance of the 0 and the 1 loop quiver. So I'll come to it later, but a representation of a quiver is just a vector space for every vertex and a linear map for every arrow. So if I have just a vertex and no arrows, that gives me these vector space, these stacks. So I need to supply no linear maps. Whereas if I have a single loop, I have to supply one linear map from the vector space at the vertex back to itself. Anyway, yes, so these are two very basic calculations in cohomological DT theory, and somehow they're the only calculations that we'll have to do.
Why is 1 plus TC? What higher term?
So I guess the annoying answer would be just from the formula, right? So 1 plus TZ is I have a minus T to the 1. So this one is a minus 1 to get this to be 1. So this number here is minus 1, but then I say minus it, and I end up with just a single. I hope I haven't made any mistakes. It's not out of the question. Whereas, yeah, so the annoying, not very illuminating answer is it's just a matter of juggling the signs everywhere. The slightly better answer is you think of this T as keeping track of cohomological degree. And so the fact that it's got an odd exponent as opposed to an even exponent is saying that here I'm meant to be taking a cohomologically graded vector space, which is one-dimensional, so it's just a 1, it's my 1 coefficient, and sits entirely in odd cohomological degree. And if I take the free supercommutative algebra generated by that, because of the causal sign rule, it'll just be 2-dimensional. So that's where this difference comes from.
By the way, really silly question is, does it have anything to do with classical exponentials?
Yeah, it's not a silly question. It does. I mean, there's a expression for the Ptic exponential in terms of classical exponentials. It's not super illuminating. I mean, yeah, there is a formula that's not on the board and that one can just put on the board for Ptic log and Ptic exponential. But I suppose it's a matter of taste. I've always found that putting that formula on the board in a talk and just saying, well, there you are, that's the definition, is not as useful as really explaining where it comes from. It comes from taking characteristic functions of supercommutative algebras.
So here T is other degree or so here T.
Yeah, so T is keeping track of cohomological degree. And here I've got a T to the 1, which is saying that this is the characteristic function of a vector space which is one-dimensional. Its kind of n degree is it all lives in degree 1, hence the exponent of z is 1, and its cohomological degree is also 1. And that's why when I take the free supercommutative algebra generated by it, I don't get much, because I'm really looking at the exterior algebra generated by a one-dimensional vector space, which is just two-dimensional. Okay, doing exceptionally badly for time now, but that's really fine. That's really fine. Okay, so the last slide. I mean, you know, I did my best. I'm not sure how well I did, but I tried to make it, tried to motivate it. But really, the motivation is on this side. This is where you kind of see the power of plathistic exponentials, or why they have a place in this talk. Okay, so this slide is going to be a passage from plathistic exponentiation to cluster mutation. So let K be the semi-group of unfrozen dimension vectors. Recall that inside our quiver we had some vertices which are frozen and some which are unfrozen. And the vertices 1 to n were the unfrozen vertices. And let K not be z to the n, but n to the n. So these are unfrozen dimension vectors with positive entries. Okay, so recall that to form a quantum torus, I just needed to give you, before I had a lattice, but here I just do the same thing. Instead of taking Laurent polynomials, I take honest polynomials. And then B is the skew-symmetric form, which quantizes this quantum ring. So here I have the same kind of thing as you saw before, defining the kind of T commutativity of this thing. Then if I send x to the gamma to y to b acting on gamma, it's back of an envelope exercise that this gives you an algebra homomorphism from this slightly non-commutative algebra into this old, slightly non-commutative quantum torus or algebra. Okay, so that's all well and good. What's the point? So it's an easy calculation, I claim, that if I is not equal to j, then if you take this thing, so recall this was, you take xi, you multiply it by some formal power series in t, and then you take the plathistic exponential. Take that expression, push it forward along this map, or the completion of this map, to get some presumably very complicated expression in terms of the y's instead of the x's. Then that expression commutes with yi if, oh dear, yeah, one of these has to be a j. Let's say this one. Yeah, let's say this one's j. Sorry. Should be a j. So if I is not equal to j, then this horrible expression commutes with yj. Certainly does not commute with yi. So now if we come to the interesting case where j is equal to y, and then this expression does not commute with yi, but if I take it, commutate with it, if I conjugate by it, I get, I mean, something that by all rights you should expect to be a horrific mess, right? So these things are these quantum dialogues, so these very, very infinite formal power series. I take one of them, I multiply by this, and then I multiply by the inverse of this thing. But because everything is non-commutative, you're meant to expect things to be a horrendous mess, but they're not. Again, I claim it's a back of an envelope calculation, that in fact this expression winds up being equal to this, which is precisely the expression that went into the definition of cluster mutation and then slightly later quantum cluster mutation. So the punchline is that cluster mutation and also quantum cluster mutation is performed by taking expressions in x. So in here, taking plothistic exponentials in here, and then letting them act on this ring by taking conjugation. And we know it works for doing one cluster mutation, but cluster mutation is an iterative procedure. So if we want to do more than one cluster mutation, you just take more than one of these expressions. And if you take a product of expressions and take the conjugate by it, that's the same as conjugating by them one by one. So you can kind of maybe believe that this is going to be able to recover not just one step cluster mutation, which is kind of boring, but arbitrarily long steps of cluster mutation, which is where all the difficulty lies. Okay. So okay, so how are we gonna use this? The answer is it comes from some technology, as I say, developed by Gross, Siebert, Hacking, Keel, Kontsevich, and others, involving things called, and Kontsevich, and Sogelman, involving scattering diagrams. Okay, so this is very definitely one of those things where if you launch in with the definition, you lose everyone immediately. But if you have an example and then a definition and then another example, I think that's the sandwich that that people are most likely to want to eat. So okay, so here L, my lattice of dimension vectors, I'm going to make it nice and simple so I can draw it on the board. And remember this lambda was the skew-symmetric form that told me how non-commutative my quantum torus was going to be. So I'm not going to set it to be 0 because that would just be saying everything's commutative. Nothing interesting happens. But I'll do the next most boring thing. I'll just say it's 1. The bigger this number is, the harder the maths becomes. Okay, so this is what's called an inconsistent scattering diagram. And what's inconsistent about it is if I start here and I want to end up here, we've got essentially 2 ways of doing it. I can track around this way or I can track around this way. And if every time I pass a wall, that's what these things are called, every time I pass a wall, I just, let's say I start with a 1 here, and every time I pass a wall, I multiply whatever I have at the moment with whatever sits on the wall, so this function. Then doing this route, I multiply by this, and then doing this route, I multiply by this, and then this, and those things are not the same. Those 2 ways of multiplying those 2 walls together, but given by the 2 orderings, are not the same. That's because I'm working in a mildly non-commutative quantum torus. So this is called inconsistent because different ways of getting from A to B results in different things. But it's really easy to fix. You put 1 extra wall in, you put this function on the wall, and now this is consistent. No matter which way I choose to get from here to, say, here, be it by going this way and multiplying first this, then this, or this way, multiplying first this, then this, then this. That gives me the same thing, and that's called the pentagon identity. Okay, so just to give you some feel for how desperate things very quickly become in this story, here's another inconsistent scattering diagram. And all I've changed here is I've made this skew-symmetric form that controls the non-commutativity a bit scarier. So now this is inconsistent for the same reasons. And this is what you have to do to make it consistent. You no longer get away with adding just 1 wall. In fact, you don't even get away with adding, I mean, you add infinitely many walls. And what's more, there's a whole region here where the walls are dense. And that's what you have to do if you want this to be consistent. If you want it to be the case that this path from here to here gives you the same product as this path, you have to have infinitely many walls. So that's, but the, yeah, the kind of goal of the game is to add in extra walls to make things consistent. And it can always be done, but often with some pain, as you can see. Okay, so what are the actual definitions underlying these pictures? So a wall in a scattering diagram, like what we had before, is a pair where this thing is a n minus one dimensional rational polyhedral cone in the realification of my lattice. And it's parallel to the perpendicular to some p in n for my bilinear form. So yeah. So these are like hyperplanes, but with some bits missing, because I don't ask for the whole hyperplane to be in my wall, but just some rational polyhedral cone, but it's lodged inside this hyperplane. And it's called incoming if closed under adding BP. So like forewarned, the definitions are very difficult to chew through in real time, but just the pictures I have in mind is that these walls that sort of stretch back to negative infinity, those are the incoming walls. So a scattering diagram is a union of walls in LR. So on the wall, we have some function, and that function is a function in T, this quantum parameter, and x to the p, where p is the vector which is sort of determining the hyperplane that the wall sits in. And a scattering diagram is just a union of such walls. And we do make some technical assumptions, but I'm not going to spell them out. Okay, so that looks a bit loose. There's not much meat on that, but we'll get to it. So the joints are the kind of non-generic bits. So the bits where these walls meet, or the bits where the walls have a boundary. So those are kind of special non-generic parts in the scattering diagram. Now, take some paths, so some embedding of the interval from 0 to 1 into the kind of ambient real space that this scattering diagram is living in. And we're going to ask that it avoids this nasty locus. So again, to go back to the picture, that would just be saying, avoid here, don't go here. That's bad, but everywhere else you're allowed to go. Okay, so given a path avoiding the joints and crossing a certain number of walls a certain number of times, so these t's are limits in here, then here's the operator we assign to this this path. Okay, so these were the operators that we were using to check for consistency. And the thing that made a scattering diagram inconsistent was that I could have two paths with the same endpoints, such that the operators built this way by taking out of the function sitting on the walls could be different. So these are the sort of the things that test for consistency. So yeah, D is called consistent if these functions, these operators only depend on the endpoints of gamma. And like I said before, this is really the same as asking that the products of these functions be the same no matter which way round we go. So as a result, in various levels of generality, due to Gross and Siebert and Kontsevich and Slobodan, that every scattering diagram can be made consistent by adding a unique up to equivalence set of outgoing walls. So that the outgoing bit is important. We could have made this diagram consistent by adding another wall that is precisely the same as this wall, but with the function just minus x to the 0, 1. And then, yeah, in fact, that would already be consistent, but that would be a pretty boring way to win the game. So we have to set the game up so that that's not allowed. And the way you do that is say you're only allowed to add outgoing walls. And then the theorem says you can still do it, but you might end up drawing a picture like this.
Question for the Kontsevich argument is I remember, for example, in the crossover program, they need to handle this zero order intersection. So when because the Kontsevich solvent only works when you can produce higher order wall.
Yeah.
So I think in the crossover program, the most important one of the important argument is they need to keep track of the order.
Yeah.
Of the wall.
Yeah.
And so, for example, just in this situation, what is the definition of the order, so that you can make consistent scattering diagram?
I mean, so sorry, the exponents p that appear in the definition are living in this this thing here. Yeah, and here I can give this thing the order given by, let's say, the sum of the entries, and do things order by order that way. One way to, I mean, these two-dimensional examples may be misleadingly simple, but one way to convince yourself that actually this is true and almost obvious is that what are we trying to do? We started off with something that was inconsistent, and it's inconsistent because if I take this times this and compare it to this times this, I get something different. So what you do is you just take their difference and check that the difference appears in order above 1. So then that tells, whatever that difference is, that kind of tells you what to put in on the middle ray, the thing with order 2.
In this case, I remember the Ptic example is the just commutator. It's the commutator.
Yeah.
The two functions. So
Right.
So that's what the order increase.
So right, if you take the commutator of these functions, you'll get something that's horrible, but it will.
Possibly. Yeah.
But the first place, and it won't be 1, right?
Yeah.
But the first non-zero coefficient above 1, for the order given by summing the entries, will be x to the 1, 1.
Yes.
And if you want to kill that, there's only one way to do it. Your hand is forced. You have to take the Ptic exponential of precisely that function and shove it on this wall. Then you take the new commutator, which is the old commutator times that correction function. And because you chose the right correction, although the thing will still not be 1, the discrepancy terms will have order 3. So you'll have something like x21, x12, and you kill them the same way. And you just keep going.
Yeah, that's why you have
Right. And for this number equals 1, that process terminates almost immediately.
I think that one, just the commutator will
Yeah.
do.
But for any higher number, that process goes on forever. But you're solving something order by order. So once you take all of them, for any given coefficient, you've shown that the thing is consistent up to the order exceeding the thing you're trying. Oh, sorry, this is not a good sentence. You show that any given coefficient is 0. Because after a while, you're only fixing things in higher order than the coefficient that you're worried about.
I think in this case, the good thing is your space is not compact. You are doing it on the vector space, is it? So the walls will come back and then intersect again.
Oh, okay, yeah. So yeah, that does make life a lot easier. Right. No problem. Where was I? Oh, yes. Okay, so that's a consistent scattering diagram. Like I say, there's the definition. Not sure how possible this is to pass that in real time, but that's the picture. That's a consistent scattering diagram. So what we do with it in order to get from scattering diagrams to theta functions is introduce another bit of kit that again needs a picture, which will come along shortly. So first, let me define broken lines. So for a broken line, I need a few bits of data. First, I need a scattering diagram for it to pass through. But also, I need to give you its ends. So Q, or script Q, will be the place where the thing ends. And P will be its asymptotic direction, so where it comes in from. Or its direction as it zooms into the scattering diagram. So a broken line with these ends is a piecewise linear path, avoiding the joints. Like I say, we never want to go through those non-generic bits. meeting a certain number of walls, finite walls at these times. So it might pass through other walls, but we just ignore. So we have a certain number of points between minus infinity and 0, called S1 to SR, such that my broken line meets these walls, W1 to WR, at those times. Between those meetings, the thing is going to be linear, and it's labeled by a monomial where the VI is going to keep track of the direction that this broken line is traveling in. Okay. So what do we require? We require that it ends up at Q. So by the time it gets from minus infinity all the way to 0, it's at its endpoint. On any one of these piecewise linear sections, its direction of travel is given by the exponent of the monomial that we've attached to that straight bit of the broken line. The monomial, as it comes in from infinity, has coefficient 1 and direction, or this v0, this exponent, which keeps track of the direction, given by p. So this is the other bit of data that we set when we define the broken lines. So the incoming ray is labeled by yp, and because of this second condition, that means that it's traveling in direction p as well. And how do these things change as they cross the walls? So as I hit a wall, there's a function on that wall. I can take add of it, applied to whatever monomial is currently attached to my broken line. I'll get some Laurent polynomial. I pick one of the monomials in that Laurent polynomial, and that's my new monomial. And because that might be a different monomial to the one I had before, as I came in and hit the wall, that might mean I changed direction, hence the broken lines. So like I say, it's so much better to have a picture than a definition for this, and so I'm going to rectify that very quickly. But let me just make a remark. So why go through this pain? This is the key thing, and it's a very elementary observation. So as long as the functions on the walls have positive coefficients, then every time my broken line goes through a wall, and whatever its labeling monomial is gets replaced by a new one, it will also have a positive coefficient. And that's obviously quite a leading fact. So let's very quickly get on to some examples. So here's the easy example. It was easy because I could make it consistent by adding a single extra outgoing wall. And here are the 3 broken lines with ends -1 to 0. So -1, 0 is keeping track of the asymptotic direction that the thing comes in from, and Q is keeping track of where the thing ends. And it turns out there are exactly 3 broken lines. So whenever I pass through a wall, there's always the option of just ignoring it. There's always the option of saying that meeting just isn't one of my SIs. I'm just going to ignore it. So that's what happens here. I just ignore all of these walls, and I just have a straight broken line. Here, I ignore this wall, but at this one, I consider what happens when I take add of this function, apply it to the monomial that sits above my broken line as it comes in, and look at that gives me a 2-term thing, and I consider the non-trivial term in that. I get a new direction and a new monomial, and then I do something similar up there. So yeah, these are the monomials that I end up. So this was my starting monomial for all 3 of my broken lines. But for this broken line, that starting monomial gets replaced by this one when I make this break. And because I've replaced this exponent with this one, I've changed the direction. So this is just something you can do. I mean, maybe a priori it's not clear that this is a worthwhile thing to do, but this is again, elementary thing you can do. So right, finally I get to the definition of theta functions. So the theta function, or the theta functions associated to a scattering diagram B, they are given by summing over broken lines in B. So this is where you get to see that a priori you probably have no right to expect these things to frequently be Laurent polynomials. You would expect, especially for that horrific scattering diagram that I had on the board earlier, you would expect, oh, well, there will just be infinitely many of these and this won't make any sense. But let's say the universe is kind in this respect. So this definition makes sense. I sum over all broken lines that have ends given by asymptotic direction P, endpoint Q, and this CL infinity is just the, or this thing, this entire monomial, is the monomial associated to my broken line as it gets to Q. So in general, this may be a formal function. Yeah, and in general, these things transform well. So if I change the endpoint of that all of these broken lines are hitting, in principle, quite complicated things can happen with the combinatorics of these broken lines. But in fact, the theta functions transform well. What's more, since I guess.
Let's do this thing with the time. We'll go until 3:30.
Yeah.
Pause for a minute. Give
Yeah.
a chance to the audience to leave, and then we.
Yeah. Okay. So yeah. So these theta functions, they look like they depend on Q. They do depend on Q, but because these transformations, as I transform from one choice of Q to another choice of Q, are all given by algebra automorphisms. Recall that these are given by conjugations by vertical elements. These structure constants, which gets me increasingly close to where I want to be with this talk, the strong positivity conjecture, these do not depend on Q. So these are something really intrinsic, these structure constants. And let's just fix a generic Q. Okay, and this is the thing that when I saw it, I realized that this really is the universe being kind. Not only are these, so if I want to express these theta functions as possibly formal Laurent power series, I get to do that using the combinatorics and mechanics of broken lines, which is great fun and a sort of interesting thing to see. But something much deeper happens. Namely, that the structure constants themselves are also given by taking sums over broken lines. So I take the sums of the products of the final monomials on broken lines, the pairs of broken lines, with asymptotic directions given by P and P prime, adding up to P double prime. So that's the structure constant I'm trying to calculate. Again, these things are given by summing over monomials attached to the endpoints of broken lines, which is really good news, because recall, one of the things we noticed along the way was that if in our scattering diagrams we can guarantee that all of the functions on all of the walls have positive coefficients, then all coefficients at all endpoints of all broken lines are positive. So this is obviously going to be a useful thing. So A mid, I said it earlier, but now let me define it. This is the ZT module spanned by theta functions such that these things are Laurent polynomials. And yeah, when you see this definition, you think, well, this thing might just be empty. I mean, the arbitrary scattering diagram can be incredibly unpleasant. So maybe these functions are just always formal. Well, it isn't. It's an algebra which contains the quantum cluster algebra. And what's more, the quantum cluster monomials form part of the theta basis. So there's a lot there, but all of it's good. And it tells us that if we want to solve or prove the strong positivity conjecture in the quantum setting, it reduces to a statement about scattering diagrams. It reduces to a statement about the functions that appear when you consistentify arbitrary scattering diagrams. Okay, so let's see. I'm just trying to work out. Yeah, okay. So this is how that goes. Let D be a scattering diagram. So before, in my examples, I always started by just drawing two walls on two hyperplanes, putting simple functions like these on the walls and then just seeing what happened, seeing what I had to do. Well, that turns out to be the sort of general recipe for what you should do. So let D be a scattering diagram with one wall for every unfrozen vertex. Before I was drawing examples where there were just 2 unfrozen vertices, but there might be more. Then by whichever version of the theorem regarding consistent scattering diagrams you choose to use, you can make this thing consistent. And what's more, once you've built this thing up into a consistent scattering diagram, you can define the theta functions, as on the previous slide. Then the cluster monomials and the structure constants we've seen are given by sums of broken lines in D+, or sums over final monomials for broken lines. So positivity reduces to showing that the functions on the walls have positive coefficients. That's where we've got to. But who has a feel for how meaningful or easy that problem is? Well, if you've gone all the way through Gross-Hack and Keel and Kontsevich, you sort of know what to do next. You do a lot of scattering diagram techniques, perturbing things, working order by order, recursive arguments, to somehow get the statement you want down to the simplest possible statement. That is where you have 2 walls meeting and your lambda is 1. So the thing that is solved by the quantum dialog, where you can just see that all of the functions on the walls are positive. Well, in the quantum setting, it's not quite that simple. You can use similar arguments to get down to a 2-wall case, which is great. But now you have to worry about T. And what's more, you do have to deal with the fact that this alpha 1 might not be 0. So you have essentially two different cases for each one of them. And also, we can't reduce to the case where this number n is equal to 1. The argument in the classical setting that enables you to do that just doesn't work in the quantum setting. So using the same ideas as GHKK, we can get down to a simpler statement, but it still involves 4 times infinity cases to work with, including the n equals 3 case, which was already brutal. And as you can imagine, n equals 4, 5, 6 don't get any nicer. Okay.
Just pick a good time to pause.
Yeah, I'm trying to remember what. Well, yeah, comes the punchline and then I'll come back to an example calculation. So, yeah, so the theorem goes by showing that for the consistentification of the cluster scattering diagram, indeed, all of the functions on all of the walls are positive. And that goes by reducing to those 4 times infinity special cases and using some Donaldson-Thomas theory. Yeah, that's hard, but it's somehow standard by now. And the upshot is the following theorem: that there is a subset of the lattice and quantum theta functions indexed by that subset, such that each one of these things can be written like so. So it's what's called pointed. So it's kind of lowest term is y to the p, and then there are some sort of higher terms. And here's the first bit of great news. This looks like the usual quantum positivity statement, that all of these coefficients are positive. So this does indeed recover my old result about positivity for quantum cluster algebras. This thing is closed under multiplication. It really is an algebra, as is this. So this is quite a confusing way of saying that the strong quantum cluster positivity conjecture is also true. If I take a product of positive linear combination of these things, I get, again, a positive linear combination. That is, the structure constants are positive. And what this has got to do with cluster algebras is that this set contains all of the cluster monomials. And yeah, let me stop there, actually, or at least break there. So this, yeah, this is the quantization of the GHKK result, and it says precisely that the interesting thing about it is that this set is the same as their set, in fact. The points in the lattice corresponding to quantum theta functions, which are not strictly formal, are exactly the same points as the points in the lattice which correspond to usual theta functions, non-quantized, that are not strictly formal. So it's the same size as the GHKK algebra, except it's now defined over this slightly larger coefficient ring. And it's, yeah, the quantum version of their result. And yeah, I'll stop there. Thank you very much for your patience. And
Let's say that's the end of the official time.
yeah.
Let's take some questions and then we continue. Is there any question?
You say you mentioned DT invariant, right?
Yes.
Negative, or what is L for DT invariant?
Yeah, so the story there is that we're calculating or considering DT invariance of the category of representations of the quiver. And DT invariants are, there's one DT invariant for every dimension vector of the quiver. And dimension vectors live in that lattice L.
Not DT invariant for variety.
No. No, in fact, yeah, nothing that difficult. DT theory for quivers with no potential is easy.
Is there any more question?
Something in the chat, but maybe that was someone saying we can't see. Oh.
So here the theta function, right? So you construct a theta function, right?
Yeah.
That is the coordinate function of the middle variety, or I think the paper, right?
Yeah. I mean, the reason I'm pulling a face is that everything is quantized, right? So yes, but in a sense that one has to be a little bit careful with. I mean, something has to give, right? Because they're not commuting with each other. But that's right. I mean, the original GHKK or gross Siebert, this is to do with intrinsic mirror symmetry, where these things are meant to be in certain cases simply are the ring of functions on a mirror.
I think in this case, it's a theta function over some polynomial generated by the some second homology class, right?
Yes.
If I,
Yeah, in that picture.
and second homology class corresponds to the deformation of the middle parameter. Or,
I'm not sure how to answer that.
So I think you may know in the Grossi-Berg case, they interpret this type of walls as or symplectically, they are supposed to be like mass of index zero on this.
Yeah.
And so that's already like one type of quantization. Like from symplectic perspective, they are like quantum symplectic information.
Yeah.
So, and you are further quantizing that. So, is there any reasonable guess they may relate it to higher genus invariant?
Oh.
It's a very vague.
No. That's no, I know the answer is yes, and I can tell you where to look, but I can't give the answer in real time.
Oh, so the answer is indeed they.
Pierre Bousseau has this thing,
Yeah, exactly. Yeah.
some interpretation in terms of higher genus.
Uh-huh.
Yeah, okay, I would have to look. Sorry.
So what's the difference from what Objective Solomon described, right? In the famous case, right?
Oh, the cluster transformation
Yeah, yeah,
stability
yeah.
conditions and
Different or
yeah, so what did they do in that? Well, they did a lot in that paper, but as regards cluster algebras, so let's see.
so you also contact, right?
Yeah.
like this.
Yeah, so I don't want to misrepresent anyone's work. So this right. So this observation that conjugating by a quantum dilogarithm is one way to recover cluster mutation and quantum cluster mutation. Of course, purely algebraically, that's classical, but interpreting that as a transformation you get via wall crossing, this is in there. This is in the Kontsevich-Solomon paper. I presume for the first time. Then yeah, and that's just one cluster mutation. I think you do have to then go into the subsequent literature to get a fully worked out story of how to use Donaldson-Thomas theory to perform iterated cluster mutation. This is certainly worked out at least classically in Kentaro Nagao's paper on cluster algebras. I can't remember the title. And then subsequently developed further by Hyun. But in the original Kontsevich-Solomon paper, the sort of ones I would again, this is not doing justice to even this portion of their work, but the sort of fully worked out version of one-step cluster mutation in terms of Donaldson-Thomas theory and change of stability condition. That's the thing there.
That is L is full commodity, right? That is L.
Yeah, well, that would be a different part of the same paper, but yeah. Yeah, that's okay, that's getting into the bits of the paper that people always get worked up about regarding which bits are fully worked out and which bits require extra components that either didn't exist then and were developed subsequently or not. A sort of full story of motivic DT theory for coherent sheaves on a Calabi-Yau threefold. That's something a little bit sensitive. Whereas here, just dealing with quibbles, it's much more smooth sailing.
Do you wanna go on or have like 3-minute break?
I'm happy to just go on.
Okay.
It depends. Do other people want to break?
Oh, let's just go on.
Okay. Okay. So yeah, so right. So here was the point. We could kind of copy a lot of what GHKK did. So what we want to show is that if you start off with a very simple scattering diagram, the one in bullet point 1, you make it consistent, then the only things you see on the walls are positive functions. And we could reduce that to an infinite number of applications of a simpler looking statement, which is that if you just have two walls coming in and with these monomials, on the walls, then all you see coming out is positive. If we can do that, then we're good. But we saw before that the question of whether this exponent is even or odd makes a drastic difference to what we get out here. So we're not going to be able to reduce from 0 and -1 down to 0. We're going to have to consider both the even and the odd cases, both the bosons and the fermions. And also we can't reduce to the case where this number n is equal to 1. We have to deal with n 3 or greater, which is, given the scattering diagram for n equals 3, maybe a slightly terrifying prospect, but that's just going to have to happen. So I've got here an example to show you a different kind of horror. So the example I had before had this number equals to 3, which is very bad, but I didn't have a t in here. So I had a fermion meeting a fermion. But now I'm going to have a boson meeting a fermion, but with this nice number here. And the point is, this is still bad. So I'm going to go through the procedure that I sort of babbled through earlier of going order by order. So the first thing I do is I introduce this new wall so that this thing is consistent at least up to order 2. But it's still inconsistent. So I have to add another wall with another function on it. And it's still inconsistent. And in fact, same kind of nasty thing happens. You get that once you go through all of the orders, you'll get that every single rational slope between here and here has a non-trivial wall. And that's just because I changed this coefficient from 1 to t to the -1. I kept my lambda as 1 to try and make life as good as possible, but still, it's a mess. So this is here to convince you that something pretty heavy is going to have to come in to save the day here. And the thing is Donaldson-Thomas theory. So in general, what are we trying to do? We're trying to solve this factorization problem. This is just in algebra what I had in pictures on the previous slide. I have this product, and I reverse the order of it. So this term comes to the front here, this one goes to the back. And then I have to put in terms here in order to make this product, to make the left-hand side equal to the right-hand side. That's the job. And once you've expressed it this way, you can kind of see that it must be possible, but it just might be grim. Okay, so here's how we do it. So you let Q be a quiver with vertices 1 and 2, minus alpha as the I loops at each I. So this is where we break the golden rule, but never mind, let's just press on. You have possibly a loop at either vertex and n arrows. So n was the number recording the non-commutativity of my quantum torus. So that's some fairly simple quiver. And we get the following. That whatever this function is here can be written in terms of quiver representations. That whatever this function is, it's the generating function of the stack of semi-stable representations, the dimension vector passing through AB. So it might be AB, or it might be 2A, 2B, 3A, 3B, whatever. And I take the sum of all of those for n greater than or equal to 0, take the characteristic function, and I guess this is in this form minus this extra kink. This is due to Reinecke. That these functions, which are a priori fairly mysterious, can be written in terms of quiver representations. And this is exactly where an old theorem of myself and Sven Meinhardt comes to the rescue. So we proved that the right-hand side, this thing, is this thing. It's you take some BPS AB. So this is just written as this is the intersection polynomial, essentially, of some possibly singular vector space, but it's the polynomial of the characteristic polynomial of an actual cohomologically graded vector space. So simply because vector spaces don't have negative degrees, this thing is positive, it has positive coefficients. So that buys us precisely what we want, that all of these functions appearing in the middle, and yes, there might be infinitely many of them, but all of them have positive coefficients. So that's it. That's where the Donaldson-Thomas theory sort of saves the day and tells us that indeed all of the functions appearing on the walls in the consistent scattering diagram will all be positive. It comes from this thing called the integrality conjecture. It's one of those weird ones that carries on being called a conjecture. Okay, so this side I've shown you. And yeah, so the final two sides are just some sort of, what next? It seems like the problem has pretty much been flattened. What to do next? So this is the sort of aftermath. So going beyond quantum positivity, recall the definition of quantum n, and recall that we call positive linear combinations of such polynomials Lefschetz type. Then they have two origins in life, or in maths at least. If a finite dimensional vector space V carries an integrable SL2 representation, and we take its characteristic function, so we go through the weight spaces with respect to the Cartan, take the dimensions and record them in this polynomial, then because, well, it's, what do I want to say? Well, quantum n, for n going from 1 to infinity, those are the characteristic functions of the simple integrable SL2 representations. So it follows that this polynomial must be a sum, a positive sum of quantum numbers. So therefore, if a polynomial arises this way, it's of Lefschetz type. That doesn't really explain the name. This explains the name. If X is a smooth projective complex variety, then the shifted Poincare polynomial, so here's the shift. I've just shifted it so that it's symmetric around the origin. This is of Lefschetz type, and this follows from the hard Lefschetz theorem. The hard Lefschetz theorem tells us that there is, I've shifted the grading of this vector space so that it's symmetric around the origin, and the hard Lefschetz theorem tells me that there's an isomorphism between the minus ith piece and the ith piece via a sequence of morphisms that pass through all of the ones in between, the same parity. So you can get from that to the claim that this shifted Poincare polynomial is of Lefschetz type. That's where the name comes from. So that's what the future direction is. So recall the strategy. We started with some scattering diagram, which was very simple, but then we consistentified it, not a nice English word, but there we go, which might produce a horrific scattering diagram, which we can nonetheless define theta functions with respect to. And out of that gadget, we get all of the cluster monomials and all of the structure constants. And so positivity reduces to showing that the functions on the walls are positive. So we use that if the functions on the walls are positive, then all broken lines have positive end monomials. And it's possible to show an analogous thing, that if all of the functions on the walls are of Lefschetz type, then all of the theta functions are of Lefschetz type. So it's kind of tempting to suppose that the following is always true. So ignore this. Then what we proved is that the quantum theta functions satisfy this additional property. Not only are they positive, but all of these coefficients are of Lefschetz type. Again, this generalizes something I proved a few years before. But this is under this annoying assumption that Q is acyclic, meaning that there are no oriented cycles in Q. And yeah, we conjecture that this is true for general Q, but it's been a few years now, and I'm no wiser for any reason why this might be true, except that a computer tells me that it's probably true. Okay, so thanks a lot for your extended patience, and here I really will end the talk. Thanks.